Hello, hello, hello. Testing, testing. One, two, three. Hello, hello, hello. Testing, testing. Hello, 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 hello. Testing. Okay, hopefully that doesn't pop so much, but sorry if it does, as always. I didn't have any better recording stuff. I haven't done this for a while. I think the last time I looked heavily at some quantum mechanics was s- uh Sunday or Sunday, I think, Saturday and Sunday. So I wasn't on here. What I did do was um I got through to the end of this because it actually doesn't have a another exercise. So if you were to look back to the previous one, I was trying to understand this, and um, it ended up being quite easy. And actually, I think just for the record, I will go and get that. Yeah, I actually finished my little notebook. I think I did at least. Yeah, I finished the notebook. Um, on such a cool problem, right? Uh, let's see, what did I do? So I went through and tried to find out how um, you went from this to this, basically. Um, and there was just a lot of working through the problem basically of trying to find. Let's see. Let me see if I can remember. I don't think I really need to recall it so much, but essentially so show how to go from the basis to the orthonormal basis. It was that you recalled back to this. And if you have a basis and you want to go to an orthonormal basis, uh, this one here, then you take the vector and you divide it by the magnitude, where the magnitude is equal to the square root of the inner product, and then you get your vector here, and that actually works. For the second, it was exactly the same, and for the third, I think it was exactly the same, but there was just a bit of confusion because my ratio, uh, the ways of like doing ratios and stuff was not good. But I did get it in the end, and it was interesting. I remember that. Um, actually, I think I did. I actually think I did it. Um, I did a little bit of that on the laptop, to be honest. On my tablet, sorry. Let me just double check this. It's possible. Yes, it's possible. That's shorts and triangle equality. That's the next part. So yeah, I think I did that on here. So let me just double check that because that'll be interesting if I did, and then I can actually just show it. It's a shame this is so slow. Let's see. Oh yeah, I did it here. Great. Okay, so um, basically I just I worked through it and then I found out that you're doing because you're working with fractions, you have to just be very careful with the way it all works. I don't really remember the rules of it, but I got it in the end. So actually it looks like Yeah, that was a good place to stop. And I think I focused on the Schwartz inequality, Schwartz and triangle inequalities, um, which I believe I started to ask questions about, but I think we're going to start from there because I actually don't really remember anything about that part. So, but I remember about this kind of question here. So go back to here and move my little dots. I probably won't stay on for so long. A little bit tired, but I really want to convince myself to have a crack at this again. So I wanna just sip my tea and I'm ready. Ah, okay. So Schwartz and triangle inequalities. Two powerful theorems apply to any inner product space obeying our axioms. Theorem 5, the Schwartz inequality. Here it is, that the magnitude of the inner product is always less than or equal to the multiplication of the two inner products. Ah, yeah, I actually did this as well. I did this at the pub, actually. Um, yeah, so I did. Let's imagine that you had um, v equals. Let's just do it. So I said, imagine that v equals 2, 3, and w equals 1, 1. Then the Schwartz inequality says that the magnitude is always less than or equal to the multiplication of the separate magnitudes. So then I did, well, if VW is equal to, sorry, uh, let me just think about this. Yeah, so the inner product is equal to 2 times 1, because it's 2 times 1, etc., etc. I'll just write them out. And it's an inner product, so we plus them together. I think I did 3 times 1. And then we had equals 2 plus 3, which equals 5. So the inner product was 5. Let me just double check this, because I think I remember I made a mistake somewhere. Um, I see. No, I didn't make a mistake on this part, at least. Um, okay. And so then the magnitude of v is going to equal the square root of v, right? So then we have, which is equal to, let me just double check this. Yes, exactly, yeah. So I did is equal to the square root of 2 times 2 and then plus 3 times 3 because we're doing v by v, so it is what it is. And then which equals, I'm not going to do this myself, but I've already done it, that's why 4 plus 9 equals the square root of 13. And then I did w, so let's do that. W is equal to the square root of w and w, and so we just multiply by itself, so it's going to be is equal to the square root of 1 times 1 plus 1 times 1, which is equal to the square root of 2. And then I did the magnitudes together, so therefore if we multiply these together it's going to be, let's see, well, it's going to be square root of 13 plus, sorry, multiplied by square root of 2, which apparently here is roughly 3.61 times 1.41, which equals 5.1. So that's what I did, just for reference. And so indeed, the magnitude of 5 is less than or equal to 5.1, and 5 is less than or equal to 5.1. Because this is this, and the inequality is oh, it's the magnitude of that, sorry. So, oh yeah, okay, but um, if you were to take the magnitude of 5, it's going to be 5. So that's correct. So that proves that one. We agree. And then and I started on the next one. I did use the same stuff. Um, so let me just see which is okay. So this is the one before, and then we do v plus w is less than or equal to v plus w, which is the triangle inequality, right? That's what that is. And so if we calculate that, we get v plus w is equal to 2 plus 1 and then 3 plus 1, because um, we're just taking the vectors here, 2 plus 1 and then 3 plus 1. Yeah, you can see that. Cool. Which equals, of course, 3, 4. And so the magnitude of 3, 4 is equal to the square root of 3 times 3 plus 4 times 4, which equals the square root of 9 plus 16, which actually ends up equaling 5 apparently. And so 5 is less than or equal to 5.02. I'm guessing 5.02 is going to be these ones added together. Maybe I was a bit more accurate at this point or something like that, but that's essentially what I've done here. Okay, yeah, I think I was a bit more accurate with it, so let's just do that. And then we moved on to the next one. So it says the Schwarzschild inequality is one of the powerful theorems, and the triangle inequality is the other one. The proof of the first will be provided, so you can get used to working with bras and kets. The second will be left as an exercise. This is where I think I started to go through it, and yes, I think I didn't complete this one. So let's start from here then. Okay, good. Uh, for reference, this is all the stuff. Cool. Bye bye book. Done. I just tried to put the inside in, the pen in. Of course, this is my tablet pen. Idiot. That's that. So let's go on, and I'll put my little dots here again so I can line up the screens. Cool. So it says before proving anything, note that the results are obviously true for arrows. The Schwarz inequality says that the dot product of two vectors cannot exceed the product of their lengths, and the triangle inequality says that the length of a sum cannot exceed the sum of the lengths. This is an example which illustrates the merits of thinking of abstract vectors as arrows and guessing what properties they might share with arrows. The proof will of course have to rely on just the axioms. To prove the Schwarz inequality, consider axiom 1i applied to this, okay? So the vector is equal to the another vector minus the inner product of that vector with yet another one over the magnitude of that one squared multiplied by the vector itself. Okay, let's start with that. Therefore we get let me get my little cursor here so you can see. Therefore we get the inner product of z. Well, let's try it ourselves. This is quite interesting. It says, so z is equal to v, and it's inner product, yeah, inner product of w and v over the magnitude of w squared multiplied by w. And it's interesting because this w squared, actually, this part reminds me of the magnitude it's of, not that one, but I guess it is 1i or li or whatever it is, 1i, let's see. It reminds me of this one. So it's looking like we're going to get, if we go back again, 1, but we're not in this case because we're doing a different vector. Okay. So the inner product of is it z? Yeah. Is going to be equal to let's think about this. This is complex. Let's just take a little interim here. So if I start with just doing what I know so far, that w squared, w is equal to the square root of the inner product of w. So we can do that. So let's put that in place now. So that therefore w over v over the square root of w squared. Like this. Let's move that along a little bit. So therefore that equals that. But this is squared, so let's go to the next step. So z is equal to v. Oh man, I hate being an idiot with the placement of things. It's going to be w v, but it's actually just going to be over the inner product of w. Because if we square root it and then square it again, we we get back to the start, right? The square root of something is that, and then you square that, so that's fine. And then that's going to be multiplied by w, right? And so that's quite simplified. But then we've got that's interesting. So I don't know the rules for, because these inner products are just real numbers, so you would essentially have some number divided by some number, but they are completely different numbers, and then you're going to multiply it by the vector itself. So you're scaling this vector by that inner product and by the initial vector. So let's see what this is saying then. I see. So this actually keeps with the squared down there. So it's saying that the inner product of z is equal to an inner product of, well, okay, this is really interesting, this. Let's go here. It's saying that we start the v, then we minus wv over w squared w. So that's the left side. Let me just put a little thing here. Let's get the right side out. So I'm very interested in seeing how that actually worked. And how might one do this themselves. W. So let's actually replace these with red. That is an interesting inner product, right. Now why would we want to do that? It says this is an example which illustrates the merits of thinking of abstract vectors as arrows and guessing what properties they might share with arrows. The proof will of course have to rely on just the axioms. To prove the Schwarz inequality, consider axiom 1i applied to that. Consider axiom 1i. I tell you what, let's just ask GPT. I don't want to lose my place, and I feel like I'm going to lose my place here. The book. Oh dear. Yeah. Okay. The book states that we should consider axiom 1i applied to z equals v minus w v over w power of 2. I guess I need to put these in brackets like that. And then that multiplied by w. What is that axiom again? Let's see what happens. It's very slow. I really apologize. I've actually asked yeah, a question about it basically. So hopefully they can solve this at some point. So I do not have the specific content of the book. So I tell you what, let's what is actually again, because leads on to provide a proof um, for Schwarz inequality. It says we get Z equals V minus W V divided by W to the power of 2. Let's do that. W, and then that, and then V minus W V divided by W to the power of 2 W, etc. Let's see what that says now. Oh no, error generating. I can't respond at the moment. Oh, here we go, here we go, here we go. Oh dear man, it's so laggy. Oh, I tried Edge browser as well in desperation. Please work better, you know. But no, it's not a happy puppy. I mean, maybe it's worth trying to move chats, like create a new chat. But I don't really understand how far it goes back in the context of your chat. So I don't know if that's a good idea, basically. So it says, the formulation you provided appears to be part of the process of orthogonalizing vectors using the Gram-Schmidt process, and is a step towards the Cauchy-Schwarz inequality. In the context of quantum mechanics, the axiom 1I is likely one of the postulates or axioms fundamental to the subject, but without a specific reference to the book or source you're referring to. So it doesn't even know, right? So let's try and new this chat up. Let's create a new one. I'm reading the Principles of Quantum Mechanics by R. Shanker. I'm at Schwarz and triangle inequalities. The book states that we should consider apply to yeah, let's just see what happens. That's so much quicker already. Oh yeah, that's so much quicker. So, provides a comprehensive overview of quantum mechanics, and among the axioms presented in the book, axiom 1I refers to the rule about the inner product of state vectors. The rule is stated as follows. Axiom 1I, to every state of a physical system, there corresponds a unique ket in Hilbert space, and to every ket there corresponds a unique state. The ket and bra are said to be the Dirac joules of each other. Furthermore, the inner product of two state vectors is given by this, and it possesses properties such as linearity, conjugate symmetry, and positivity. Given this background, you can understand the expression z equals that, where z is some state vector and is a complex scalar. Yes, we understand this, and we even talked about it. To get the expression you mentioned, this expression is essentially the inner product of z with itself, which gives the squared magnitude or norm of z. By evaluating this expression further, you can proceed to prove the Schwarz inequality. Right, yeah, and it's actually doing that though, which is an important result. Okay, so it knows what we're talking about. That's good. Um, so where do we go from here? Because I actually quite like to figure out how it gets to that next step. because we have two very specific inner products. Um, this is, I see. So both sides are equal. Um, so it's actually, this is the same uh, as this, and this is actually just this. Not quite. The only difference being is that the V has been negated from it. So we, oh no, hang on. Oh, so I wrote this down wrong. Okay, that's good. Okay, so this makes a lot more sense now, right? So this has actually got a minus. So this whole thing is actually equal. That makes much more sense now. Okay. So they are exactly the same, right? So it's saying just take silly me. Yeah, I can waste a lot of time to be honest because I'm an idiot. I'm a fucking idiot. One day I'll get better. So it's just saying let's take the inner product. That's a bit boring. Fair enough. And we can think of the inner product as this as well, the actual state of the above is like that, but it doesn't seem to help. So they're just saying then that the inner product of, so this is the inner product of z is equal to that, and then it's saying which is equal to, well, this would be an interesting thing, the inner product of v, and I can see how that might be relevant because if I just go and circle this for a second, I can see that this vector that's not working. Now Microsoft Whiteboard's not working. Here we go. This vector and this vector um, magnitude together, so you could do like terms here, couldn't you? Because you've got it's putting the negation of this part, negation of that part. Oh wow, okay. It's wonderful, isn't it? It's really wonderful how it kind of manipulates it all. Um, Let me just consider this for a second. So the WV is swapped with VW, which is interesting. WV, and the W is no longer on its own. So this was multiplied by W here, but now it's WV multiplied by VW because the that's interesting. Let me see if I can. Yeah, that's better. This is interesting. It's saying the inner product of V minus. So you've got this square down here, but it's decided to multiply this, and it's not plussing them. So timesing this by W. Whoa, okay. Hang on a second. I need some copycatting here again, because I need to circle things. So let's see how this is done. V W V V W over W squared minus the same, but one's the conjugate. W V conjugate multiplied by W V over W squared. Just going to move my screen along for a second. And that makes that equation. So let me just neaten this up a bit. Oops. Oh no, come on, Microsoft Word. Whatever it is. You gonna do it now? There you go. Right. So what are we doing here? Let's see. So we start with this term, and even more so, we start with this term, like that. And if we multiply that by W, the inner product of V minus the scaled version of the it says the inner product is equal to the sum of IV. Just check my blood sugars. Okay, we're starting to go up. I had a pizza, so I've had my normal injection and I have to kind of offset, like, because the carbohydrates I guess kick in. Let's go for a 3 uniter. Injection. Um, I'm not high yet, but it's going up. It's going up. Yeah, I think what I'm missing here is that I'm having to recall back to this. So this actually talks about Dirac Jules, and I suspect we actually Dirac spaces. Technical point here: the inner product is a number we're trying to generate from two kets V and W, which are both represented by column vectors in some basis. Now there is no way to make a number out of two columns by direct matrix multiplication, but there is a way to make a number by matrix multiplication of a row times a column. This has the feature that the answer depends on which of the two vectors we are going to convert to the row. The two choices, VW and WV, leading to answers related by complex conjugation as per axiom 1H. So, 1H, axiom 1H. And this is saying that the vector can be written as that, or the conjugation of it is then the bra of it. So there's something to remember there. Then we've got this, suppose we wish to expand a vector in an orthonormal basis. To find the components that go into the expansion, we proceed as follows. We take the dot product of both sides of the assumed expansion with J, or J if you're a purist. So the inner product of this is, I can't remember this stuff, but the find, i.e. to find the jth component of a vector, we take the dot product with the jth unit vector, exactly as with arrows. Using this result, we may write the sum of, yes, we found out that that was equal, and so I multiply by the inner product of that which was summing. So basically, the vector is equal to the components of the vector multiplied by the base vector, I think it was. No, yes, no, it's multiplied by the ith vector. So you've got this vector is equal to the sum of all components of V multiplied by the component of V multiplied by the vector V is equal to the sum. You're going from I to infinity, and so V is a component of that vector. So it's equal to the sum of all the components of the vectors multiplied by the ith vector. So that leads on to say that therefore the inner product of the J being, we take the dot product of assumed expansion with J, or bra J, let me just look back through my notes here, because I'm pretty sure, it wasn't too long ago that we did this. I guess it would be about here. Let's see. Let us see. I'm not seeing any sums of here, so it's not that. It's probably a little bit earlier, so let's try the fourth. I can see a sum of, okay. Yeah, this is it. The Kronecker delta, that's the one, yes. And the Kronecker delta says that 1 if I is equal to J. And where J equals 1, so if v is equal to that. 0, 1. That's I are the base vectors. Yeah, yeah. That's exactly what it is. I are base vectors. Okay, fine. So, in that case, do we learn anything for our current thing? So let me just go back to what we were doing here. I think it's looking like that one. So if we now understand that that's the base vectors, fine. And so there's no negation happening here. There is a single vector equals the sum of all components in that vector, but there's no components written here, so I don't think it's to do with this. Now this says, axiom 1I, to every state of a physical system there corresponds a unique ket in Hilbert space, and to every ket there corresponds a unique state. The ket and bra are said to be the Dirac joules of each other. Yep. Furthermore, the inner product of two state vectors is given by that, and it possesses properties such as, yep, we know this. Given this background, you can understand the expression that, yep, where z is some state vector and wv is a complex scalar, yep. To get the expression you mentioned, this expression is essentially the inner product of z with itself, which gives the squared magnitude or norm of z. By evaluating the expression further, you can... okay, so can you take me through the steps as to how it becomes v minus w v v w over w to the power of 2, etc., minus, etc. So let's begin with the state vector z defined by the expression that. To find the inner product, we need the inner product of z with its dual z. First write the dual. So bra is equal to bra v minus that. Oh, okay, that's interesting. Next, find zz, the inner product of it. So that would then equal the bra and ket of it, which gives us this. I see. Okay. Because of the dual, I see. Okay, cool. That's nice, yeah? And then expanding this out, you get our terms v, because it's v times v. Oh, hang on though. Because... Oh, I see. Oh, okay. Let's do this. How silly of us. How silly of me. I mean, we're definitely in this together if I can't figure something out. But I'm getting this now. So, um, let's try this ourselves. So if we're taking if you're taking the inner product, what you're essentially doing is you're going to, oops, multiply the parts of the components. So this is a vector and that's its component, right? So we have to multiply that by the 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 other one, but normally if you're doing in a product, you multiply the components together and you would plus them together if there was another component of that, but there's only one component, so you're just ending up with um, v, well, basically this times this. That looks funny. Um, and so we'll end up with, so let's see, v times v is, it's v, no, it's v in a product with v. Um, Minus WV, and I guess the inverse of this is VW. Um, is the inverse of, this is saying negative WV over W squared multiplied by WV, and then it's doing that very same thing but multiplied by VV, which is another one I'm not understanding here. Um, Actually, can you be a bit clearer in your expansion? I can absolutely understand that we're working out the inner product. So we want to multiply the um, com components together. There is only one component per side of the ket, and so we end up with uh, multiplying each side and not having to add the other add some other component together. I therefore can see the validity in VV. I can also see VV because they are um, bra and ket, and so the product of them becomes the inner product. I can also see that you would multiply negative WV with uh, its with its ket, multiply bras with its um, ket version, but in your expansion you note that it's reversed instead. Um, that's your so let's just put the numbers. I therefore can see validity in your point 1. I can also see that you would multiply bras with its ket version which is your point 2. Um, oh, I see. No, no, hang on. Because it's actually the inner product of WV, which, so it's scaling it by WV, because in this case we do that, then we do V that, which is VW, um, which is it's actually V with its ket version, that, which is your point 2, but I'm confused because wouldn't that be uh, your point 3 first? E.g. V multiplied by this, um, that, so V multiplied by that would equal and it's actually V, isn't it? That one there would equal V W, um, and this is a minus. Like that. VW minus that. So let's just double check, because I just want to make sure I understand why it's kind of um, changed the order there. You're absolutely right, and apologies for the oversight in my initial explanation. Let's go over the expansion again. Given z equals that, let's break it down term by term. V is the inner product of V with itself. Therefore, V minus that. This is the term you correctly identify for expanding. We get V W W V W W V. Notice that V, the inner product of V and W, is the complex conjugate of WV. So the product is just a magnitude squared. Oh no. What? Um, I tell you what, I will go get a drink. 1 second. This stuff's awesome. I love this. Just very subtle hint in the water. It's not sweet, but it kind of is, but it kind of isn't. It's like really nice. Yeah, let's focus down on this again. So it says, um, the inner product. This is the inner product of V. And we see that because we're kind of multiplying the size together, so we have to do, something, and then we're doing negative that. Sorry, we're doing v times this. So v times this. This is the term you correctly identified. Expanding, we get negative, because we're doing it v with that, so we're going to have a negative, but it's multiplying it, so we're multiplying wv, the inner product, by v. So you're saying that if you multiply an inner product of if you multiply a vector v by negative that, you end up with now that's interesting, because I think I may have forgotten this part, right? So you end up with this is wrong, so this is w v over w squared multiplied by the product. You're going to end up with so it'll be v times w v equals I just don't understand why. So multiplying that by an inner product, where did that rule come from before? Multiplying by an inner product. Multiplying by an inner product. But this is talking about base. So that's not quite the same. And you'll get v times w equals and it's not v, it's this one. I have to remember that because that actually makes a difference. So it's actually that. Yeah, so now we're getting somewhere because V times W equals the inner product of VW. So you're going to have VW, um, and then you're going to have this last part of the term, um, which is the W squared, right? And so how you end up with steps like 1, 2, 3, something about the magnitude of W. Let's just see what happens because I think it might understand. Let's give the expression step by step to ensure clarity. We want to calculate this. Yes, expanding this expression we will indeed get 4 terms. So V, this is straightforward, yep. V, that, when you multiply the ket part, WV, W by the bra V, the scalar in front of the ket is a constant. So you can multiply it to the result of the inner product. We understand that. Given that VW is the complex conjugate of WV, you can rewrite this as WV squared. Oh, the magnitude of. So where did we learn that? The magnitude of that is equal to the square root. Wait. Wait, 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 wait. Wait, 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 wait. When you multiply the ket part, WV, by the bra V, the scalar in front of the ket is a constant. So you multiply it to the result of the inner product. Given VW is the complex conjugate of WV, you can rewrite this as the magnitude of WV squared. Um, really now, where did we... I don't think we've come across that, to be honest. So the inner product, the sum of all the components of V with all the components of W, if you conjugate the V, and therefore the inner product of V is equal to the sum of all the components magnitude squared, the magnitude of all the components squared. So, okay, when you, so when in your part 2, you, you end up with the conjugate, the magnitude of the conjugate of the Dirac dual squared. Where in the book has it already spoken about this type of operation? I feel like it's a surprising turn of events. Yeah, because if you were to do Microsoft Word's gone, whiteboard's gone again. 1 second. Don't let me forget what I was gonna do. Come on, respond, 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 respond. Yeah. Okay. Cool. So if we were to do v times the negative of w, because we're doing this one, right? Um, then you get VW. This is clear, but it's not. Ah, I see. And then now you can multiply this by that. Ah, we do know this. When you multiply by a fraction, you multiply the top one. Um, let's just make sure of that. Multiplying two fractions together. You multiply the numerators, top numbers together, and then multiply the denominators together. After putting the two results together as a new fraction, you may need to simplify the fraction in order to express it in lower terms. Maybe not then. Okay. So now we've done that, and we get the inner product. Now this becomes yeah, v w copy. Oh, I don't know how to paste. How do I paste? How weird. You think you just click on it and it would do it. Huh. Okay. Well, I can't paste that apparently. A bit weird. Um, Basically this. So it's that and then it's that, right? And so now it's saying that because you've got these multiplied together, it says you end up with the magnitude squared because let's go back again. I'm missing something very obvious here. It's something just absolutely close to here. I I see that if you have if you have base vectors, it's slightly different. These are not base vectors, so we can't treat them as such. So I think this stuff is is not related to it. Um, so it says when in your part 2 you end up with the magnitude of the directional squared, where in the book it has yeah squared. Where in the book is it already spoken about? I feel like it's a surprising turn of events that um, WV divided by the magnitude of W to the power of 2 multiplied by VW equals magnitude of WV. Um, Magnitude of WV to the power of 2 divided by magnitude of W to the power of 2. Let's see what happens. The step you're referring to involves the relationship between the inner product of two vectors and its complex conjugate. In quantum mechanics and in general vector spaces over the complex field, the inner product of two vectors is a complex number. Okay, the relationship is AB, BA, where it's, yeah. Now if you take the magnitude of a complex vector and square it, you'll end up with the product of the number with its complex conjugate. So c magnitude of c squared equals c times c conjugate. Applying the relationship to the vectors v and w, you get this. Um, yeah, I think this is clearer because here it does not talk about this. It's simply saying that yeah, there's a very interesting difference here with the way it's explaining it here. Now we can understand now that we get VW, and so you can then multiply that by the top, and then you've got to do the same for the other one. So let's run this through the ringer. I am very much wanting to see this work out. So let's start again. We've got this. We've got z equals v minus vw over the magnitude of w squared. We've got the multiplied by w. Okay, it's working. Is it just w like that? Yeah, it is. And then that's all by the v minus vw over w squared w like that. And so you end up with the multiplication of v times, i.e. v times v, like so, which equals the inner product of v. Then you end up with, let's do this. V times this essentially, so let's write that. So v times the negative of v w over w squared, like so, equals, and you can see that it's got to have the inner product there, so it's going to be, maybe we should do this on a new line, equals, maybe like this, vw over w squared vw equals is it vw? wv. I mean, let's just do it. wv. Annoying. Don't think it matters, right? Same calculation. But regardless, it helps me to think about this and then refer back to it, not get too confused. So wv wv, and this would be definitely vw. And so now they are different, you see. So it does make a difference. That's interesting. So then you get the magnitude of wv, but squared. But actually, we actually just get wv vw over w squared. Now we're starting to get somewhere, right? So that's that left part. Now we need to do this times v. So it's going to be this times v. So wv over w squared w times v equals wv over w squared, and then oh no, wv, which this time is different because they're the same. So to multiply them together, we're taking a conjugate like this. Now, I don't know why. I don't know why. It's the conjugate because it was property negative. I've forgotten the negative here, so this is going to be negative multiplied by positive v. I I think I'm sort of following along. Let me clarify by going through my steps and asking questions along the way. 1. Z, oh dear me, is equal to V minus W V divided by W power 2 W, and then V minus that V WV, sorry, divided by magnitude of W power of 2 W. So let's just double check this. You've got V minus W, inner product of W and V divided by the magnitude squared multiplied by W, V minus inner product of WV over W squared multiplied by the W. Okay, cool. 2. Because because we are doing an inner product, we multiply the two vector sides. We multiply the bra and ket together. Normally, we would then we would have to multiply each component of the vectors and then sum them together, but in this case there is the vector is just one component, so it ends up simply being the product of the two, of the bra and ket. So therefore it's going to be V times V equals V. We can do the following because they are constants on each side of the equation, and are not tightly coupled with anything else. So now we've got 3. So it's going to be V times negative of this. V times negative of this, actually. Now, so what do we say here? Because we are doing an inner product, we multiply the bra and ket together. Normally, we would have to multiply 2. Therefore, 3. We can do, so now 4. Now we move on to multiplying the first bra constant v with the ket side's negative part, which equals wv, which equals this, but we're going to do that, VW. So here is my first question. Why do we not multiply the denominator by the v as well? Okay, so actually that's a good place to stop. The term that is scalar. Scalars can factor out of inner products. So when you compute the inner product, the scalar term can be factored out, and you'll be left with here VW is the complex conjugate of WV. The product of a number with its complex conjugate gives the magnitude squared of that number. So VW equals magnitude, but to address a specific question, the denominator is just a scalar, like the term WV. When you distribute the bra across the terms in the ket, scalars will naturally factor out. This is a key feature of inner products, especially in the context of complex vector spaces like quantum mechanics. In other words, V is being distributed across the terms, but the scalars from the ket are pulled out in front of the inner product. Here, what do you mean by factored out? There's a way of saying that you can treat the scalar separately when you're performing operations, especially in the context of vector multiplication or taking inner products. For example, when you scale A multiplying a vector V, like AV, and you take the dot inner product of this with another vector W, you have WAV equals AWV. Here, the scalar A has been factored out of the dot product. It's as if you first take the dot product between W and V, and then multiply the result by the scalar. In the context, okay, hang on. W dot product and AV is the same as have a scalar a multiplying a vector v, I see, then it's just scaling that, so you might as well scale the whole thing because you end up multiplying the components, I see. Um, in the context of the quantum mechanics and the Dirac notation, if you have a scalar c multiplying a ket, like c ket, and you take the inner product of this with another ket, you get c and that. You can factor it out because if you, is this right? You can factor out because if you scale v first by some number, by some factor, by some number, and then take an inner product, you end up multiplying with the vector you're doing an inner product with. So any initial scaling of one number, e.g. a with v, becomes scaled with w in the end anyway. Consider two vectors v and w in some vector space, and let's say you scale v by some scalar a. If you take the dot inner product of a v with w, it would look something like this. Expanding the dot product element by element, you'd get is w1 av1 plus w2 av2 plus 3. You can see that scalar a multiplies each element. Now factoring a out, w1 plus v1 these equals a wv. Here wv is just the normal dot product between w and v without the scaling. You anticipate when you scale one vector and then take an inner product with another vector, the scaling simply factors out and multiplies the result of the inner product between the unscaled vectors. So if you, yeah, okay, fine, it's fine. So if we go back to our original question, we've got to the point where wv, why do you not multiply as denominator by the v as well? It says the scalar term can be factored out, and you'll be left with the negation of that times that, we know that. So here v and w is the complex conjugate of wv. The product of a number with its complex conjugate gives the magnitude squared of that number. So vw times wv when you say about the complex conjugate being the magnitude of the inner product squared, in the book it actually doesn't bother converting that. It sticks with saying w v w v. W power 2. I think that's one cause of my confusion. If you're happy with this, then I can continue. If the book is keeping notation as without converting to, that's perfectly fine. It's just a choice of notation. The important thing to understand is that the product represents the magnitude squared of the inner product. Typically for clarity and brevity we might write this as, but it's the same thing. The important thing to understand is that the product of the two inner products represents the magnitude squared of the inner product. So the next question is, so rewriting this, let me try again. We only multiply W, multiply by the, multiply W V W, sorry. Ah, it's WV. Fucking hell, what is it? V and then V times that is, which equals we only multiply the nominator wait, what's the top of a fraction called? The numerator, numerator, that's the one. Numerator by V, because the magnitude of W. Oh, is it because of that? Because the magnitude of W is equal to the square root of W. Um, and so if we are going to multiply it by V, V by W, because it's been square rooted and then squared, hang on a second. Hang on a second. I'm getting something here. Let me just focus out a little bit because I'm getting somewhere though. I'm feeling this now. Let me just zoom out. Move about here. Yeah, that's probably so when I lean over you just don't see the top of my head all the time. Nothing else. If I was to multiply by the bra the inner product of W, like that, you are um, it may seem strange that the denominator does not get multiplied, well, which equals w squared times v, which equals negative w w, because the magnitude of w equals square root of w, and that squared equals w. Good so far? Correct, v equals v. This is where the meat of the expression happens. When you distribute the v across the terms in the ket, you get v times that. Using your explanation minus that, your understanding of w squared is also correct. The magnitude squared of a ket is self. Your expression seems good so far. You will just continue with these steps to fully expand z by multiplying out all terms in the bra with all terms in the ket. Okay. So write this, let me try this again, because and um, here's a question. Why in the book does the w to the power of 2 remain as w to the power of 2? In my equation, I could have equals, or so how does the denominator continue to just be when we need to multiply it by v? That's the question, isn't it? You set out when you're taking in a product. Yep, okay. Say we have a bra and a ket CB, where C is some scalar. When you're taking in a product between a bra and a ket, you can treat scalar quantities as factored out. Yeah, we got that. But notice how the scalar factors out of the inner product operation. The inner product operation is strictly between V and W. The fact that the denominator can just be W2 is a consequence of this factoring out. You're not directly taking the inner product of the denominator with anything. Rather, the denominator is a scalar coefficient that scales the result of the inner product. So the book keeps it as W2 because it's a scalar factor, and you can indeed represent it as either W2 or W, depending on the context or the step in your calculation. But surely that surely missing the multiplication of the scalar affects the end result. It's the difference between, for example, a 1 denominator of 1 and a denominator of a vector scaled by 1 by you're on the right track by identifying the importance of scalars and the role in mathematical operations. However, let's break this down. When you're dealing with the inner product, it behaves linearly with respect to scalar multiplication. Let's work with your example. Suppose you have a scalar a and vectors a ket and b and bra b. If you take the inner product, this is a fundamental property of inner product. The scalar can be pulled out of the inner product. Now, let's take your specific scenario. Here's the crucial part. That scalar is not undergoing an inner product operation. It's just a scalar multiple of the actual inner product operation, which is between v and w. In the mathematical expression above, the scalar multiplication and the inner product are two distinct operations. The scalar simply scales the result of the inner product. So to address your concern, the difference between a denominator of 4 and a vector scaled by 4 only matters if you're directly taking the inner product of that denominator with another vector. The calculations you're working through, that denominator is behaving as a scalar coefficient, scaling the result of the actual inner product. In quantum mechanics and linear algebra in general, scalars can freely factor in and out of inner product calculations without directly undergoing the inner product operation themselves. The square root of, so if you have a vector and you've got its magnitude, right? So the magnitude is going to be a number, and then you're squaring that number. Your above vector is going to be divided by a larger number. So the vector becomes smaller. I still don't understand. I don't like to dismiss things like things in a, oh, it's a quantum mechanics thing, so don't worry. And I know you're not meaning to do that, but I feel like that's what's coming across. Basically, if I take 1 or 2 divided by 3 multiplied by 2, in the case of this book, it's saying, no, don't worry about multiplying that denominator by the vector. Just do 4, 4 divided by 3, rather than 4, 4 divided by 4, 4. Well, oh, sorry, not 4, 4. 6, 6. Well, one answer, well, the first answer, the answer from the book would therefore be 4 divided by 3, 4 divided by 3, whereas my expectation would be 4 divided by 6, 4 divided by 6. And these come out as very different coordinates, right? So I still don't understand. I don't like this. In the case of this book, let's imagine it showed numbers instead of letters for vectors. It would therefore be saying let's see what this says. Appreciate a bit of attention to detail. Your example helps clarify the point of confusion. Let's address this with your numerical example. Given 2, 2, 3 times 2, 2. First, let's address how scalar multiplication with vectors works. When you multiply a vector by a scalar, every component of the vector gets multiplied by that scalar. 3 times 2, 2 equals 6, 6. Yeah. So that's just do. Well, the answer from the book would be therefore, but whereas my expectation would be, okay, so I must have done something wrong, but 3 times 2, 2 is 6, 6. So now when you're talking about the operation 2, 2, 2, 3, it seems as a misconception. Division of a vector by a scalar is just another way of describing scalar multiplication. 2 over 3, 2 over 3, that's what I did. So when you compute, it becomes 2 over 3, 2 over 3, times 2 over 2, 4 over 3, plus 4 over 3 equals 8 over 3. Your second example, where you're effectively trying to divide the vector by another vector, is not a standard operation in vector arithmetic. In the realm of quantum mechanics and linear algebra, vectors don't get divided by other vectors in this component-wise manner. To sum up, the scalar in front of the ket or bra behaves as a simple scaling factor affecting every component of the vector uniformly without the need for component-wise division. This is why the result in Shanker's book may seem like it's neglecting the scalar factor during the inner product, but it's actually correctly factoring it out. Given 2, 2 times 2, it would be 3 times 2, 2, which would be 6, 6. Did I not do that? 6, 6. And so now when you're talking about the operation 2, 2, it seems there's a misconception. Division of a vector by a scalar is... So this has got a bit confused, right? It's fine, but let's see. I think it's telling us something though. A vector by a scalar is just another way of describing scalar multiplication. So when you compute that, it becomes 2 over 3, 2 over 3 times 2 times 2. So it's going to be 2 times 2 divided by 3 is 4 over 3 plus 4 over 3. Wait, so you're wait, so you're saying when you multiply a fraction by a number, another number, you only multiply the numerator with that other number. When you scale a vector by a scalar, you multiply each component of the vector by that scalar. Multiply a fraction by a whole number. If you have the fraction 2 over 3 and you want to multiply by 4, you would have 2 times 3 equals... Yeah, that's exactly right. I hope you understand that your point 1 is the actual answer to my entire confusion. I actually thought you did 2 times 4 and for the numerator, and then 3 times 4 for the denominator. Therefore, 2 over 3 times 4 equals 2 times 4 over 3 times 3. That's where my problem lied. It's actually 2 times 4 over 3. Noting that you don't multiply the scalar 4 by the denominator part fraction. And so now I can clearly see that that minus WV VW divided by that is correct. This is what it says. I'm glad we could get to the root of the confusion. Yes, when you multiply a fraction by a whole number, you multiply the numerators together, and then the denominators together separately. In the case of multiplying a fraction by a whole number, the whole number is effectively over 1, so it doesn't change the denominator. Oh man, see, wow, that's like GCSE, right? So there you go. You understand that's now correct. Glad to see you understand it's translated correctly. Beautiful. It's essentially a over b times c is actually a over b times c over 1, and so that's why that ends up being the 1. I think we've done this before. I've made this mistake before. Anyway, so that clarifies that. So let's go back to our explanation because I think we're getting close to the end then. So in my equation, here's a question: why? So which equals this, like that, right? And it's important to note that the denominator is not necessarily is multiplied by 1 because the v is a scalar, and as a fraction it would be v 1. So now moving, so now it's going to be 5. So now I need to take the conjugate, right? Because we've done this part now. This is what we just talked about. 5. We now move on to multiplying the bra's negative part by v by v, noting it's the Ket's side v. Therefore, we end up with negative of that is going to be WV WV, but it's worth noting that when you multiply two inner products that are the same together, are they the same? They're not the same because they're the bra and the Ket version. Two inner products, one which is from the bra and one from the Ket, you end up with a you end up needing to conjugate the two. So actually, the above should be this. 6. Now we have all the parts. This is going to be z equals, and we've got the negative of this minus the conjugate one. So 7 we can simplify this. We're nearly there, guys. This is amazing. I'm so proud of myself for doing this. I'm GPT-4 is amazing. Like, to be able to just bat ideas on it and I kind of get into the webs, and if you're just convinced enough to keep trying, it's just a wonderful tool. What an amazing thing. I'd never be able to do this without it, because I wouldn't be able to follow along. There's no way to kind of challenge the kind of ideas at my level. It's amazing. So now we've got this equation. Z is equal to the negative of W V V W over W squared. That looks like transpose. Let's just and then correct that. Take away the WV conjugate of WV over W squared. Now, because we're taking that away, wait, that can't be right. Yeah, we've missed one. We've missed one term because we've done this. Now we need to do yeah, I completely was. So we've done this times that, but we now need to do this times this. So 6 is actually now for the final part. It's going to be the bras that is that right? WV over W squared, yep, times the kets multiplied by the kets that, whoa, which equals, well, let's see, we're going to have WV times W, so it says, wait, let me try this myself first. So this is going to be in the final term, but not quite there yet. Let's move that down for a second. So we need pink. So this is the blue one, right? Let's do that. And we're going to do the pink one. Which will be WV over W squared W V over W squared. Let me just make sure of this. Do I need to bring over that W? No, we don't. But it's negative negative, so it's a plus. So it's going to be, we're going to plus them together, so which equals WV W squared plus WV W squared, which equals two negatives, which equals W, let's just do that, plus that, which equals, well, W to the power of 2 plus W to the power of 2. So if we did 2 squared and then 2 to the power of 4, it's 4 to 4 is 8, and 2 to the power of 4 is sorry, I'm so sorry. I'm so sorry. Oops. 2 to the power of 4 is 16. So these are different. Yeah, 2 to the power of Oh, hang on. 2 squared is 4, yeah. That's right, 4 plus 4, yeah. So why is it then W4? Yeah, it's not this, it's actually bra W as well. So this is a little bit off. I think I need to still carry across that term. So if I do that, so I'm going to pull it along a bit, and then if I do um yeah, let's just put that in. So it's bra W, and then this would be ket W. Yeah, which will actually equal W V W V W W over W squared. And it's a positive because it's a thing. Is that, did I get that right? I got that right! Yes! I got that right, guys! Yeah! And W squared times W squared. So if I do 2 squared times 2 squared is 4 times 4 is 16. Yeah! We got it, guys! We got it! This makes sense, dude! Yes! We totally stoked. Oh yeah, I totally stoked it. Yes. Oh my god, that's brilliant. What a wonderful feeling. Let's so 2 negatives equals this, but it's actually these brackets are needed. Oh man, this is amazing. W, which equals um W V conjugate W V, which equals, so notice the conjugation because one side was bra and the other ket, and they were the same terms. And this is going to be times W W. Notice the inner product of W because one was bra and one was ket over magnitude W squared. Notice how the denominator continues to stay the same. Notice how the two negatives equate to a plus, positive. And what's this going to be? This is 7. Now we have all the parts. That equals that equals Yeah, actually, 7, we can simplify uh, wait, no, hang on, so it's minus, so they equal plus. We are plussing them together. Hang on. It's 1 times, so negative that, a negative, take away a negative is a positive. So why is that W4? No, I don't understand the W4. Um, oh, because it's not a scalar at that point. Notice the W4. Notice that the W2 becomes a W4 because in this aspect we are multiplying that bottom component with... No, we're not. We're not actually. Why does that become W4? I thought I had that, but it's actually not. It's not actually that. So this is the pink part, right? We're doing the pink part here. No, we are multiplying them. Of course we are. Yeah, we're multiplying them. That is a multiplication there. It's not just minus. We're just multiplying a minus with a minus, right? Yeah, that does make sense. And notice that W becomes because in this act we are multiplying that bottom component, that denominator with a fraction part that isn't just 1. 7. We now have our full equation of z equals that minus that plus w v conjugate of w v w w over the magnitude of w4. Yes. Okay. Yahoo! Greater than or equal to 0. 8, it states that this whole operation must be greater than or equal to 0. Why is this? Why does it have to be greater than or equal to 0? Because the whole point of inner products is always, it states the whole operation must be greater than or equal to 0 because we are working with inner products as the... Is there any other reason as to this that I've missed? Okay. Yep, so starting with ZZ, we get that. When we distribute, we'll end up with these three terms, as you detailed. Yep. Well, it's not squared, it's the conjugate. I must have written it wrong. Um, Rather than signs, it's worth noting that the term 2 is negative due to both terms in the expression being negative. You've noted this correctly in your steps. For step 8, your statement is correct. The result of an inner product must be non-negative because its correspondence to the square of the norm, or length of the vector. Physically, the inner product of a state with itself is a consequence of the properties of the inner product in a Hilbert space. This condition could be used. Once again, great job. Okay, cool. Yes. Okay, right. So we've got the last part here, and it's getting very late. Where it says where we have used antilinearity of the inner product with respect to the bra using WV conjugate is equal to VW, we find the inner product of V is greater than. Cross multiplying by W squared and taking square roots, the result follows. Excuse me, I'll have to do the exercises another time. So that's awesome progress. Um, I'm pretty proud of that, I have to say. That is so sick that we just did that. Epic. Oh look, I'm still be right back, idiot. Who cares? Who freaking cares? Alright, that's really exciting. I really want to do the rest now, but I need to relax. I've been working all day. Have a good evening, guys. Morning, guys. Whatever you want, guys.